Alright, so, I'm gonna try live streaming the lectures instead of recording them, because when I record them, I will have to edit them, and usually I'd have to do many repeats because when I'm editing them, I'll find out that I have a lot of mistakes or like um there are parts which I thought I could explain better. So I would usually repeat them multiple times, and it's I can't continue on that way because that just takes up too many time. So I'm gonna switch to a quantity over quality type of thing. Just try it out. And yeah, live streaming is the way to do it because I don't have to bother editing. I don't have to bother uploading. It'll just be all direct. Um, we're gonna start a new series today. It's gonna be about set theory. I know I started like many series, like the nervous system one, and like I just can't continue doing it consistently because of the reasons that I said before. So hopefully live streaming will make things work out, and it there's a higher chance that I can do things more consistently if it's live streaming instead. So we'll see if it works. So we're starting a new series on set theory. Now you may have a familiar understanding of what set theory is. You've probably learned it at school before. Set theory is basically the study of objects which are known as sets. So then begs the question, what are sets? Well, sets are objects which wait, they're not really objects. They are a collection of objects. So that's what sets are. So for example, I could put the numbers 1, 2, and 3 into a collection, and that is what it would look like. I'm just gonna make the 3 better because it will look like the brackets. There we go. So this is a set. It's a collection of the objects number 1 object, which is the number 2, and a third object, which is the number 3. So if you put these 3 objects together and you put them into a collection, this will be a set. This is the set containing the numbers 1, 2, and 3. Similarly, I can create another set and I can put the objects A, B, and C inside of them. And this will be a new set. It's a set which contains the letters A, B, and C. And similarly, we can also have, infinite sets. So I can have the set containing 1, 2, 3, 4, so on and so forth. So this is the set of all whole numbers, positive whole numbers, or in other words, the natural numbers. This is how we define the natural numbers. And that is, what we mean by the natural numbers. Similarly, we can have sets that contain other sets. So let's say we have the set containing the number 1 and the set containing the number 2. These in themselves are objects, so we can collect them together. So this is the set that contains the set containing 1 and also the set containing 2. Right? So the objects inside of these sets are this and this. So you contrast them to this, right? You may get confused, like what's the difference between the two? Well, over here, 1 and 2 is what makes up this set, whereas over here, these two things make up this set, right? And this is obviously different from this, right? This is the number 1, this is the set which contains only one object, which is the number 1. This is the set containing one object, which is the number 2. So these two things are inherently different from one another. Another thing you should be aware of is the notation that we use to describe whether something is inside of a set or not. So if we have an object X and a set A, then in between them we put the letter epsilon. And this basically means that X is inside the set A. So this is how we describe whether or not something is inside of a set or not. Instead of writing the entire sentence, X is inside the set A, we can just write, well, 3 symbols. We can just put these 3 symbols together, and that's obviously much easier to convey. So for example, right, these are just arbitrary objects. These are not concrete examples. So let's give a concrete example. We can have 1 is inside the set containing the numbers 1, 2, and 3. Right? Aside from 1, we could also have 2. Right? 2 is also inside of that. And we can also have 3. 3 is also inside of this set. If you have the number 4, then 4 is not inside of this set. So this is a false statement. This turns into a false statement, because 4 is not inside of this set. Right? So how do we say when something is not inside of the set? We draw the epsilon and then we put a cross mark over it. I think, yeah, like that. From, how do you call this? It's like this direction, not this direction. So it's from left to right. You cross it from left to right. Like that. So that's the notation that we use. Next is also another bit of notation. How do we describe infinite sets? Well, we did it before by doing this, but this is a bit ambiguous, right? Because, well, your brain will automatically like complete or finish the pattern for you, but sometimes the pattern is not so obvious, right? And we won't know what the set actually contains, because maybe there are 2 different patterns that match, or 3 different patterns that match, right? So we need to be more precise and explicit whenever we describe sets which contain an infinite number of things. One of the ways we can do that is something known as the set builder notation, I think. So how does that work? Well, let's give an example. Or no, let's start with an arbitrary case. So it looks something like this. And we have P of X. Right, so what this means is basically, well, collect all the elements. Oh yeah, they're called elements. So anything that is inside of a set is called an element of that set, right? So collect every element of A, right? Which basically means collect every object that is contained inside of A. But we just use the word element to make things simpler. So we don't have to say objects contained inside of, right? Contain every element of A. Wait, collect all the objects containing, no, Jesus. This is why my videos are super cut up, because I mess my words up pretty frequently. So you line up every element of A, of the set. Jesus. I'm so bad at this. Line up every element of A, right? Line up every object that is contained inside of A. And basically check whether this condition is true or false. And if it's true, then you let that object in. Well, you can think of it like as a bouncer analogy. So you have objects that are inside of A, the elements of A, let's say x1, x2, x3, so on and so forth. And then you have a bouncer over here that checks whether this condition is true or not. Maybe P of X is greater than the age of 21, and they'll go to each guy over here, check their ID, and if they're greater than 21 years of age, then they'll let them in to the club, right? So maybe after a while, you will get some elements here that made it pass through the test, and then you'll have some elements that are left behind that fail the test. So this basically is the set which contains these objects, right? Only the elements of A which satisfy the condition P of X. So that makes things a lot more concrete and explicit. So how can we use this? For example, let's say we want to describe the set which contains even numbers. So 2, 4, 6, 8, blah, 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 right? People can easily identify this pattern, but let's just assume that the pattern is not immediately identifiable, right? Then how can we convey the idea that this set contains even numbers without like being ambiguous over here, right? Because a pattern can be interpreted in multiple ways, and some people may see that it's even numbers, another person may find a different pattern that matches as well. So how can we be explicit? Well, what do we want these to be? Well, we want these to be the natural numbers, right? 1, 2, 3, 4, 5, and so on and so forth. And what condition should they satisfy? Well, we want only the even numbers to make it through inside of the club. So what we can do is we can let the condition, this is the natural numbers, right? We can make the condition be X is even. Okay? And this bouncer will check each number. Are you even or not? No, you're not even. Are you even? Okay, you're even. 2 goes inside. Are you even or not? No, you're not. Okay, tough luck. Next, are you even or not? 4, yes, you are even. Okay, I'll put you inside, and so on and so forth. And eventually, or not eventually, like, I don't know, when you're dealing with infinity is a very weird concept, and we'll talk about infinity at a greater depth, because like if you imagine doing this forever until infinity, like you're never going to finish or stop or end, right? And that is like the source of like many different paradoxes and stuff. But let's just say that we're able to complete this job, then what you'll have as a result is the set containing all of the even numbers, right? So this is basically a filtering process, right? These are the collection of objects, right? And this is the instructions on how to filter them, right? Which from these collections of objects do you want to keep, and which from these collections of objects do you want to disregard, right? On the right side over here is the instructions on how to filter it. On the left side is what you're filtering. Okay. So that's the set builder notation. So that you don't have to rely on patterns and you can avoid ambiguity. Right. So now that we get all that prerequisites out of the way, let's start with the actual theory. Okay. Why is it important? Well, it's important because it turns out that all of mathematics can actually be thought of in terms of sets and their relationships between one another. So that's pretty interesting, and we'll slowly try to uncover that. But first, we need to start from the very, very basics. And what do I mean by that? What I mean by that is we have to start at an axiomatic level. So we have set theory. It's a theory. What are the axioms which define that theory? Let's talk about the axioms. So there are a bunch of axioms that we'll have to cover, and we'll cover 2 of them in this video, but obviously there are a lot more. The first one is the axiom which I forgot what it's called. Hold on, let me look up my notes as to what it's called. it's called the axiom of extension. So I'll write it down, axiom of extension. So, well, I hope you guys are familiar with the ideas of axioms and what they are and stuff. Axioms are basically statements which cannot be proven, and that's because these are the initial or beginning assumptions that we're making in order to produce a theory. Okay. And from these assumptions, we'll combine and use them in clever ways to generate new statements from. Right, so these are the initial assumptions that we make. Therefore, there is no grounded basis for them, right? Because they're just purely assumptions. Okay, these statements can't be proven. They're not supposed to be proven. It's just something that we come up with in order to create or describe an idea or a theory, right? So basically someone came up with the idea of sets. Hey, what if we have a collection of objects and then we have this stuff and this stuff and this stuff? Okay, let's figure out which axioms can... let's figure out what are the axioms I need in order... Jesus, this is hard, okay. And basically what they did was, let me figure out the axioms that are needed. Jesus. Let's figure out the axioms which can describe this idea or model this idea in my head. Okay? I know this doesn't make sense because I'm explaining this terribly, but hopefully it will after I provide some examples. So what is the axiom of extension? The axiom of extension is an axiom that is used to determine whether or not two sets are equal. Obviously, that would be favorable. We need to identify whether or not two sets are equal. Okay. And how do we do that? Well, the axiom of extension basically states that two sets A and B are equal, right? If and only if. So this is the arrow, the double arrow, and this is used to indicate if and only if. I'll also assume that you have a bit of familiarity with logic, and so you know what like this symbol or this symbol means. So basically they are the same if and only if every object that is inside of A is also inside of B. And this symbol over here means and. Every object that is inside of B should also be inside of A. Right? So basically, this statement means that two sets are equal if and only if they contain the same objects. So let's give an example. We have the set 1, 2, and we have the set 1, 2, and 3. Let's see if they're equal or not. Okay, so both of these statements need to be true because we have the and symbol over here. So we need to satisfy both of these statements. How do we check if these statements are true or not? Let me just write A and B over here. Right? So everything inside of A needs to satisfy this statement. So we can use the same bouncer analogy again. We'll line all the elements of A, and we'll have the bouncer over here. And what he'll do is he'll walk up to each element and he'll check whether this thing is true or false. If it's true, then they make it into the club. If it's false, then they don't, right? this statement means that everyone inside of A needs to satisfy this condition. So everyone needs to successfully enter the club. Okay, so let's see if that's true or false. Okay, bouncer walks up to number 2. What will he check? He'll check if 2 is inside B. Is it inside B? Well, yes it is. Okay, cool. 2 made it into the club. Bouncer walks up to 1, asks if 1 is inside of the set B. Is it inside of B? Well, yes it is. So 1 made it through. So everyone made it through because this is all of A. And so this statement over here is correct. I'm just going to put green check mark over there to indicate that. Alright, but are we done? We're not done yet because this and this needs to be true. Alright, so let's check the other one. So now, well, these two statements are different because if one of them is true, it's not necessarily that the other one is true as well, right? Even though they look pretty similar, flipping these letters around does make a big difference, as you'll see. So now we're checking if everything inside of B is also inside of A. So now, instead of lining up the elements of A, we're lining up the elements of B. The elements of B are trying to enter the club. So we have 1, 2, and 3, bouncer, and now the condition that the bouncer is checking is also different. Over here, the bouncer checks whether the object satisfies this condition. Now the bouncer is checking with this condition instead. So he walks up to the number 3, and he checks if 3 is inside of A. And no, it's not. So 3 has to get kicked out. Bouncer walks up to 2. 2 makes it in, pretty easy to see that. Bouncer walks up to 1, 1 makes it in, pretty easy to see that. Is this statement true or false? Does every object of B, did every object of B successfully make it into the club? No, because 3 did not make it into the club. So even if 1 and 2 make it into the club, this statement is false because we need everyone to make it into the club, right? Therefore, right, so if we have 1 correct and 1 false, then this is the same thing as false altogether. Well, it's basically like, computer science. Like you have, it's the AND gate and OR gate, right? So if you have an AND gate with 1 and 0, and then you put it through an AND gate, that will output 0 because an AND gate requires both inputs to be 1, right? So that's the same thing in logic over here. If it's an AND statement, we need both of it to be true in order for the result to be true. But since both of them are not true, right, this one's false, then the overall output is false. And so we know that A and B is not equal to each other because this entire thing is false. There we go, right? So what are examples of sets which are equal to each other? Well, we can have 1 and 2, and we can also have 1 and 2. If you repeat the procedure that I did before, lining up the elements of this, checking whether they're in here, and lining up the elements of here and checking whether they're in here, you're going to find out that everyone makes it into the club. Everyone here makes it into the club, everyone here makes it into the club. It's pretty easy to see that. You can try that by yourself if you want to, but we don't have all the time in the world, so just this is true. Okay, these two sets are equal. Now you may be wondering, why do we need this axiom in the first place? Isn't it obvious? I don't need to use this procedure, this bouncer lining up procedure thing, to determine whether or not two sets are equal. I can just visually see it for myself. Well, you can't just chalk it up to like your intuition and logic whether or not something is equal or not, right? Because you could get ambiguous cases. For example, we can have the set containing 2 and 2, and let's ask whether or not these two sets are equal, right? This set contains two objects, but they're both the same objects. This set contains one object, but it's the same thing, right? This is the number 2, this is the number 2. It's just how many copies of the number 2 are inside of the set. Now, how do you use your intuition here, right? You can be like, oh, well, this is different because this has two things inside of it, this has one thing inside of it, so maybe they're different. But then again, aren't they basically the same thing, because it's just one thing contains 2, the other thing also contains 2, so maybe they're the same, maybe they're not, who knows, right? So there is a source of ambiguity, and introducing an axiom will eliminate that source of ambiguity. Right, so let's see whether or not these two sets are equal based on the axioms that we have set in place. Let me take a drink. All right. Let's say this is A, let's say this is B. Right, so what's the procedure? We're going to line up the elements of A. Bouncer walks up to number 2, checks if it's inside of B. Well, 2 is inside of B, so okay, you make it through. Goes to the other guy, he's also the number 2, so basically it's the same thing, right? Bouncer walks up to the number 2, asks whether 2 is inside of the set B or not. Yes, it is. Okay, check. And so this, the left one, is correct. Okay, let's do the right one this time. Okay, so we just have 2, just one copy of it. Bouncer walks up to the number 2, asks if it's inside of the set A. Is 2 inside of the set A? Well, it clearly is. It doesn't matter how many copies there are. 2 is inside the set A. Even if there's 3 copies, 4 copies, 5 copies, whatever copies, doesn't matter. 2 is inside of A. And so 2 makes it into the club. And so the right one is correct as well, because everyone made it into the club. There's only one person in the line. And even if one person made it into the club, that counts as everyone, because everyone is this one person. Okay, so it turns out that they are equal, right? Right, there's no ambiguity there anymore because we're following the axioms, right? A person can't say, well, there's 2 copies in one and 1 copy in the other. They must not be equal. Well, no, I'm not going to follow you. I'm going to follow the axioms that we have set in place, right? There's no room anymore for ambiguity or for different perspectives, right? This is the definitive answer now, right? We have now determined that multiple copies of the same object will not affect whether or not 2 sets are equal, right? So we could have 2, and we could have an infinite copies of 2, for example, and that will still be the same as this object over here. These 2 sets will still be equal, right? So that's one result that we have obtained from the axiom of extension, right? So the axiom is like just an assumption, and we're going to basically use that assumption in order to develop, multiple theories. So one theory, for example, the one that we have just uncovered, is that multiple copies of the same object won't change the equality of the sets, right? It won't turn the set into something different than the original if you add more copies of the same object into it. So that's one way that you can interpret the axiom of extension, or use the axiom of extension in order to create a new mathematical statement. And the more axioms we introduce, the more results we can create, the more interesting those results will be. Right, so that's a good thing, the axiom of extension, and I hope, or hopefully you have an understanding of that. Now, one thing I will note is that the statement here itself, it can be abbreviated or simplified as we say that this symbol over here is called a subset. So A is a subset of B, and over here we can have B is a subset of A. So this is not a new thing. This is just basically a way to write down the top part without using too many symbols. We instead simplify everything to this instead. So this has the same meaning as that, and that has the same meaning as this. We just prefer to write this way because it's faster. It's more simple. So you may have, because you've studied set theory before, maybe encountered this. And a very common way that people teach subsets is, well, if you have the set B, then A is a subset of B if A is contained inside of B. So you could have, like, this is A, this is B, and this statement corresponds to this diagram. The fact that A is literally inside B, you can literally see that. So if A is, for example, the set containing 1, 2, and B is the set containing 1, 2, and 3, then, yeah, this is, well, this, well, how do I explain this? Well, all three of these are equivalent, right? This is equivalent to this by, definition. We just agreed that these set of letters or symbols combined together will mean exactly the same as the letters above of it. And this diagram over here, the fact that A is literally inside of B, agrees with the statement above over here, because the statement above asserts that everything inside of A must be inside of B, and if A is literally inside of B, then this statement over here is automatically satisfied. So this diagrammatical representation is or does hold true. Okay. And it doesn't matter if it's 1, 2, 3, or you can even put like A, B, C, or whatever. It just always works, right? Because no matter what sets you have, as long as A is literally contained inside of B, then, well, yeah, this statement above will always be satisfied. And similarly, on this side, it's essentially the same idea. This time, the set B will be the one that's contained inside of A. So for example, if B is the set 1, 2, and A is the set 1, 2, 3, then diagrammatically, it will look like this. And from this diagram, you can see that B is contained inside of A. And we have already shown that this diagrammatic representation agrees or is equivalent with the top formulaic representation. And so looking at this diagram, you can conclude that B is indeed a subset of A. Because clearly everything inside of B is also inside of A, right? You can see that notationally, you can see it diagrammatically. There are just many different ways to view things, okay? So from now on, we'll just be using this instead, this notation instead of the top part, because, well, the top one has a lot of symbols and we want to be able to save space and time. All right, let's prove our first theory, okay? So let's have a theorem over here. And this theorem states, if A is a subset of B and B is a subset of C, then we must have A is a subset of C, right? You can do this diagrammatically and it will make sense. So A is a subset of B means A is contained inside of B, and B is a subset of C means that B must be inside or contained within C in the diagram. And from this diagram, it is easy to see that this is true because, well, A is inside of C. Okay. However, we tend to not encourage the use of diagrams when we want to be more in favor with the formulaic approach to things. So let's see how that works. How can we express what we just saw diagrammatically in terms of formulas, right? And for this, and the other proofs and theorems that we'll encounter, I'll try to explain things in a game theoretic way. And what that means is, instead of uh, hmm, we're going to basically turn things into a game, and solving the game is equivalent to obtaining a proof for the theorem. This may sound weird, completely weird, but I'll try to explain. Okay, so let's say we have a statement, say for all x, p of x. It means everything satisfies this condition over here. How do we provide a proof of this? Well, we can do the same bouncer thing again, right? We're gonna line all the objects x. Maybe it's more appropriate to say, like, for all x that is inside of like the natural numbers or something, like, or it can be any set really. Basically, all of these groups of objects. Wait, no. Everything inside of this collection A should satisfy this statement over here. How do we prove that? Well, we can do this by taking all the elements of A, lining them up, x1, x2, blah, 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 and we can have the balancer go over and check whether this statement over here is satisfied or not, and they'll let them into the club. And if everyone makes it into the club, then this statement is true. And the proof of how the statement is true is done via well, yeah, basically the proof is to walk through, to show the proof, we basically have to walk through the reader or whoever is watching of like the step-by-step process that is involved. And that is like the bouncer walks up to the first element, then to the second element, then to the third element, and they can observe themselves what's going on, and maybe they'll observe that everyone makes it into the club, and if that's their observation, then that is the proof, right? That's the reason for why the statement is true. Okay, but sometimes things get a bit dicey, especially with infinite sets. So let's say these are all numbers, and there's an infinite amount of numbers. We have 1, 2, 3, so on and so forth. Then obviously it's hard to make that observation because the bouncer is never going to make it to the end of the line because there's an infinite number of people waiting to enter the club, right? So even if even if the bouncer makes it through the 100th person, and all the 100 people go in, there's still thousands, millions more to check. And so it will be difficult for a person to be convinced by looking at that, right? They can be like, oh, 100 people made it through, but they can still look at the queue that is lining up and be like, what if one of those person doesn't make it? And yeah, so it will be difficult, right? And there are techniques to circumvent this. For example, induction, right? But I'm going to come up with another way to combat this issue, and this method will be through what I said, game theoretically. So, how does the game work? Well, basically you have the list of objects that are inside of A. You put them in a queue, in a line, or whatever, and we'll have a player over here. I'm gonna name him Sal, and we'll have another guy over here, and we're gonna name him Quan. And the origin for this name is, while I was studying this stuff, I was reading a comic, and they had these two characters inside of them, and so I just automatically, when I had to think of names for the players, that just automatically came to mind, and it's stuck ever since. So that's why I'm taking another drink. Right. And how this game works is Sal will pick some guy from the list. Can be any guy, it's up to Sal to choose. Right? Maybe Sal chooses X2. And then Sal will give it to Quan. And what Quan has to do is he has to be able to show that P of, well, he gives X2, right? So he has to check whether X2 satisfies the condition. He has to check whether or not this is true or false. Okay, and if it's true, then Quan wins. If Quan is not able to do this, then Sal wins, right? And so this statement is true if Quan has basically a way or a strategy which, if he uses, will result in a 100% win rate. Okay, so what that means is no matter how many times Sal and Quan decide to play this game, as long as Quan has this strategy, then he'll always be able to win. Right? And what does that mean for Quan to always be able to win, no matter how many times the game is played? So Sal can ask for a rematch, and okay, Sal gets a rematch, and he can pick another element from the list instead. He can pick X100, X1000, or whatever. And Quan will always win regardless, right? So that means that no matter what Sal does, no matter who Sal picks from the list, Quan will always be able to show that whoever Sal picks will satisfy the necessary condition. And that essentially is equivalent to everyone inside of A satisfying the condition. Okay? So these two things are equivalent. And basically, the proof will be presented as the strategy that Quan uses. If we can show that there is a strategy that Quan can use, then you or whoever else is, or whoever is watching or reading, let's say, the proof. Wait, how do I do this? Well, Okay. If I show you the strategy that Quan uses in order to be able to obtain a 100% win rate, then you will obviously be convinced by the fact that this is true. Okay, so the proof, instead of being like a normal traditional proof, will instead be written in terms of a strategy that Quan will use in order to obtain a 100% win rate. Because, well, strategy, 100% win rate, truth of this statement. Okay? So in order to explain this, all we have to do is show the audience this. Okay? Because if you show them the strategy, if you explain them how it works, if you explain why it leads to a 100% win rate, then that will also explain the truth of this statement. Okay, I hope you got that. Okay, so this circumvents the idea of infinity, right? Because we can't check every single element, right? We can't like do or watch the bouncer go through the elements one by one. Okay. So that's how this statement is proven. What about other statements though? What about this statement? Right? How is this statement proven? Well, in order to win this game, let's say these are the elements of A. What Quan has to do, this is Quan, is he has to show that there exists something from A that satisfies P of X. So what Quan does is he'll pick one element. Let's say he picks this one, and then he'll give it over to Sal. And if Sal finds out that this statement, this condition over here holds true, then Quan wins. If Sal finds that it is false, then Sal wins. And so Quan has to be able to play the game correctly. He has to be able to choose the right element from the collection of objects that is A. So the strategy here is, how can Quan figure out which element to choose in order to make this true? Okay. So that's how that game would work. And there's also, well, combinations, right, of quantifiers. Something like this, right? For any object in A, there should exist an object in B for which the statement holds true. Right, for example, let's make this more explicit because it's hard to think of this arbitrarily. Let's say P of xy is x is less than y. Okay? And let's say that A and B are natural numbers. Right? So for any natural number, there exists another natural number that is greater than, well, the original number that we chose. And obviously this is true, right? We can see that through our intuition, but how do we demonstrate the proof of it? More importantly, how do we demonstrate the proof of it with the game theoretic style, which is a style I advocate and I prefer, and that I will use to teach. Well, what will this game look like? So we have the elements of the natural numbers 1, 2, 3, and so on and so forth. So Sal. Okay, Sal what he'll do is he'll pick one element. He'll pick some element from the set of natural numbers, right? And he'll give it to Quan. And now Quan's job is to be able to find or pick at least one element from the same set for which this condition is true. Okay? And if Quan has a 100% win rate, meaning that Sal can replay this game as many times as he wants, he can, maybe this time he'll pick the number 2, maybe next time he'll pick the number 5, maybe next time he'll pick the number 1 million, right? No matter how many times Sal plays, Quan will always win. And this will essentially make this statement true, right? Because whatever number Sal picks, Quan, no matter what number Sal picks, Quan can find another number that satisfies this condition. And so this 100% win rate is equivalent to the fact that the above statement is true. All right. So but wait. Okay. Okay, this is not the proof yet. We have not shown the proof yet, right? We just explained the game, right? But we don't know whether or not there is a strategy that Quan can implement to obtain 100% win rate, that which he can implement to obtain 100% win rate. Once I show you the strategy, it will become apparent or obvious why the above theorem is true. Okay. So let's talk about the strategy here. Let's say Sal picks the number x. Okay, we'll use x to denote the object that Sal chooses from the set n of natural numbers. Right. And he says, okay, I picked the number x. Okay. Now I want you to find an element y that satisfies this condition, an element y from the set of natural numbers. So what can Quan do here? Right? Quan has to fill in the blank over here to make it so that this entire statement will be true. Well, Sal can, for instance, put in the number x plus 1, right? X plus 1 is indeed a natural number, right? If you have a natural number, you add 1 to it, the result is obviously still going to be a natural number. And so this is Quan's strategy. Whatever number Sal gives, he'll just add it by 1. And he'll choose that number, right? Sal picks the number x, then x plus 1 is next on the list. Sal chooses x, Quan will just choose the number next to it. That's his strategy, and it works no matter what x is. Sal can pick the number 1, and he'll be like, hey, okay, I picked the number 1, can you find an element that is greater than 1? Yes, I can, I'll pick the number next to it. Okay, let's play the game again. Okay, this time I'll pick the number 100. Right, what are you gonna do now? Okay, I'm gonna pick the number 101. Because 101 is obviously greater than 100. Okay, let's play again. I'm gonna pick the number 1 million this time. What are you gonna do? Well, I'm gonna pick the number next to it. I'm gonna pick the number 1,000,001. Okay, and well, that's the strategy. It doesn't matter what number Sal picks. Quan simply has to follow the same strategy. And it's apparent that this strategy works, and it's apparent that Quan will always win if he uses this strategy. And so this statement over here has been proven. It is true that whatever number Sal picks, right? Remember, this game can be repeated as many times as needed, as necessary, right? So it can account for all numbers. So whatever number Sal picks, Quan has a strategy to be able to find or choose a number that is in the natural numbers for which this statement holds true, right? And I just explained the strategy to you, and the result is an understanding of why this formula over here is true. Because we have developed, yeah, Jesus, I hope that was enough. Okay, I don't want to explain more anymore. Because we've spent a lot of time just explaining how the game theory side of thing works. But I hope it's obvious and clear, right? The point is, you can turn statements into games, and to check whether or not the statement is true or false, it's equivalent to checking whether or not there's a strategy that we can implement in order to obtain a 100% win rate. And if there is a strategy, if we can come up with a strategy, and if we can understand, and if it is apparent that the strategy leads to a 100% win rate, then that will translate to the fact that the statement from which the game is created from is inherently correct. Okay. Hope that makes sense. Alright then, so how can we use what we studied, the game theory? How can we use game theory to solve this problem? So we have a set of conditions over here, right? So if A is a subset of B and B is a subset of C, then this is what Quan must show, okay? So, okay. Let me think for a while on how to say this. Right. So, first things first. We have A as a subset of C, and that is equivalent to this, right? That's axiom of extension stuff. And so, this is what we must show is true. How do we do that? Game theoretically. Well, we can create a game where Sal chooses an element of A, gives it over to Quan, and Quan needs to develop a strategy from which he can ensure that whatever Sal, so that he can ensure that whatever Sal throws at him, he'll be able to respond with, yes, it is inside of C. Okay. Sal chooses an element of A, gives it to Quan. Quan needs to show that it's an element of C. If Quan has a systematic way to approach this problem, a way that results in a 100% win rate in the game, then this statement will be true. Okay, so, but that's not the end of the game, right? Because we have if A is a subset of B and B is a subset of C. So this means that these two things are the conditions that need to be set before the game begins, right? So before the game begins, this is just readily available information, basically, right? Because we're only considering the case where if these are true, then we need to show this, right? So in the game, we can use these as information to help us, right? Specifically, Quan can use them to help as a part of his strategy, basically. Right? Basically, if you have an if statement, then anything after that if statement, right, between the if and the then, is basically your starting or initial conditions, right, that is already, sort of predetermined, and you can use them as like information, and you know that it's true. Okay, so Quan needs to develop a strategy, and he can use this and this. Okay, cool. So let's start the game. Okay, first Sal will choose an element of A. Let's say Sal chooses X. Okay, he looks through the list of things that are inside of A, and he picks one of them, and that turns out to be X. Okay, and he'll give it over to Quan. Okay, now what will Quan do? What is his game plan over here? Well, Quan will first observe that X is in A, obviously, because Sal chose this element from the list of objects that are contained inside of A, so Quan can make this observation, right? Next, he can use this data over here, this bit of information over here. A is a subset of B. What does that mean? It means that everything is inside of A is also inside of B, right? Remember, right? This means this, which means everything inside of A should satisfy this condition, which is equivalent to being inside of B. So everything inside of A should be inside of B. And so Quan will use this, and it'll combine it with this. He'll combine these two observations together, and he'll conclude that X is inside of B. Okay. Next, what can Quan do? What's the next step? Because we haven't finished the goal yet. The goal is whatever Sal gives or throws over to Quan, Quan needs to show that it's an element of C. It's contained inside of C, right? But we're not just there yet. So what can we do now? Well, there's still this bit of information to use. How can we use that bit of information? This information states that everything that's inside of B should also be inside of C. Well, hang on a minute. We know that X is inside of B, so we can combine this and obtain X is in C. And there we have it. We just, okay, I have made the observation that X is inside of C. So you lose. Basically, Sal loses, because I have successfully extracted or made the observation that X is inside of C. So Sal loses. Okay, we can play a different game. Or no, not a different game. We can play the same game. Let's play again. Sal chooses something else, but no matter what Sal chooses, right, it's always going to be inside of A. And if it's always going to be inside of A, then it's always going to be inside of B, right? And if it's always going to be inside of B, then it's always going to be inside of C. So it doesn't matter what Sal does. He can pick this element, he can pick this element. All Quan has to do is follow this, this same procedure. Okay, you gave me something that's inside of A. It doesn't matter which element of A it is. All I need to know is that it's inside of A. Okay, so you gave me something that's inside of A. Doesn't matter what, right? You can choose anything. As long as it's inside of A, I can make the observation that it's inside of B. And if it's inside of B, then I can make the observation that it is inside of C. So you lose. I have shown that what you have given to me is inside of C. you lose. And it doesn't matter, you can play this game, we can play this game a million times, you'll always lose, because no matter what you give to me, I know that it's always going to be inside of A, and I can follow the same thought process, right? The same strategy, right? The strategy is to use this, and afterwards use this. So as long as I do that strategy, as long as I perform that strategy, then I'll always be able to end up with the observation that what you have thrown to me is inside of C. So that's the strategy, okay? And now hopefully that concludes the proof, right? Hopefully that has convinced you that this theorem is indeed correct, right? And so instead of like, because I don't think a lot of people use this framework, but I think it's more fun to think of things this way, and it's also more easy as well. It's more relatable, definitely. And all you have to do is explain a strategy, and explaining the strategy automatically gives you an intuition for why, this theorem is true. And I think that's very nice, because, everyone likes games. Games are a relatable piece of concept. Everyone's playing games these days and stuff. So, thinking of things in terms of games will obviously be beneficial. So that's the axiom of extension. We've introduced, a game theoretic framework of proving things. And we have introduced an axiom of set theory. What am I even saying right now? I've been talking for a long time, but that's it. Yeah, so sometimes I'll be using the game theoretic framework to explain proofs, and other times I'll just switch to a traditional way of explaining proofs, because obviously each has their own benefits. And what's the opposite of benefits? Advantages and disadvantages. So I'll be switching back and forth between them. And yeah, so hopefully we'll be able to continue soon with all the other axioms, but that's it for now. Thanks for watching.